Hi, this is the second of 3 videos on the right-hand rule, or the family of right-hand rules. This one has to do with the 3-part right-hand rule. And there's really just one 3-part right-hand rule, and it has to do with this equation. It relates the velocity of a moving charge, the magnetic field that's acting on the charge of the charge, and the resultant force that you get. If we look at this, these 3 things represent an axis, or a set of 3 axes. The velocity, the magnetic field, and coming out of the page at us, the force. So, if the velocity is the x-axis and the magnetic field is the y-axis, the force will always be the z-axis for a positive charge. So we're going to use our right-hand rule to figure out the relationship. So let's go through some problems. This is not actually a right-hand rule problem, but I want to draw a distinction. You'll notice that in the upper left-hand corner, I've written E for electric field. This is to distinguish between this problem, which has a B for magnetic field. Don't be fooled. Always pay attention to the field written in the corner so that you know what type of field to anticipate. In this problem, the positive charge will simply be pushed in the direction of the of the electric field. Done. With the magnetic field, the question is a little bit trickier. We've got a particle that is moving to the right. We have a magnetic field that is pointing towards the top of the page, and so the only way that I can bend my middle finger is straight out of the page, and that is the direction of the force. Now, I could attempt to draw it in some sort of 3D manner, but the official symbol is a dot, or a dot with a circle around it to indicate something coming out of the page. If you can print in colors and things, then a simple dot is good enough, but for me, when I'm using my handwriting, I usually like to put a circle around it so it doesn't look like just a random speck on the paper. All right, let's try a few more. Which way will this particle be pushed? Well, here we have the magnetic field, and it's printed in green. Hopefully that's showing up. It's coming out of the page, so we have a velocity in this direction. The magnetic field is coming out, and so my finger points this way. Now you may find that that was kind of awkward. I certainly did. So what you can do in any problem like this is rotate it until your hand isn't all cramped and weird. So velocity, field, force. Easier. Okay, actually let's rotate it back so I don't have an F in a weird direction. Here's another one. Okay, so this is a little hard to see because my hand's kind of getting in the way, but my thumb is going to go into the page to indicate the velocity. My index finger will point in the direction of the magnetic field. And then my middle finger will shoot straight out, and that tells me the force. Notice that I'm always labeling each vector velocity, force, and magnetic field. You start to get a lot of arrows on the page, and if you don't label them, you're going to get confused. All right, here are 2 more. These are slightly trickier. because now instead of having the velocity in the field, I have the force and the field. There are a couple of different approaches you could take here. One is that you can just throw out your fingers, and then you can rotate until they match everything. So I see the magnetic field is coming out of the page, and I see that the force is pointing. So the force is pointing in this direction. So which way is my thumb pointing? My thumb is pointing that way. So this must be the direction of the velocity. Now there's a second tack that you can take, and that is knowing that everything's going to be at a right angle, which means that since the magnetic field is coming out of the page and the force is going this way, we know the velocity, or at least the key component of the velocity, has to be along that line. So there are only two choices. We could have a velocity that points in this direction, or a velocity that points in that direction. We've got 50-50 odds. So if we randomly pick one and then test it with the right hand rule, we will, if we're right, we're right, and if we're wrong, we know automatically the opposite one is true. So let's say that I make a guess that the velocity is pointing in this direction. So I go V, B, uh-oh, my middle finger is pointing to the southwest instead of to the northeast. That tells me that this is not the direction of the velocity, this is the direction of the velocity. One more version here. Okay, so which way is the magnetic field pointing? Once again, we can use this elimination process. Since the particle is being pushed this way and the velocity is into the page, that means that the correct magnetic field has to be along this line. It's either pointing down or up. So I'm going to make a guess. Let's just say that it's up. So my velocity goes into the page. I got to do something with my force finger here, and look, my thumb is my index finger is pointing up towards the top of the page. That means that my guess was correct, and yes, indeed, that is the direction of the magnetic field. Now, technically, that is not strictly the direction of the magnetic field. The magnetic field is all this tells us, this force, is that there is a component pointing in that direction. So we might actually have any of these magnetic field vectors, and we wouldn't be able to distinguish. But knowing that the key component is pointing up is good enough most of the time. Okay.